In winter, the UK's weather can flip from mild and wet to bitterly cold. And one of the most powerful forces behind such a swing is something which happens high above our heads. Sudden Stratospheric Warming, or SSW. Yes, a warming in the stratosphere tens of kilometres up can lead to harsh cold weather for us. But how does that happen? Today we'll dive deep into the science behind SSWs, why they matter for our winters and what they might mean for the future. Setting the scene. Layers of the atmosphere. Before we talk about SSWs, let's understand where they occur. Earth's atmosphere has layers. The troposphere, up to around 10 kilometres, where our weather happens. The stratosphere, from 10 to 50 kilometres above the Earth's surface. This is where the ozone layer sits and where SSWs occur. Above that, the mesosphere and the thermosphere, but they're for another day. The stratosphere is usually calm compared to the turbulent troposphere, but in winter, over the Arctic, something fascinating happens. As it's tilted away from the sun, the air above the pole becomes extremely cold, with the temperature in the stratosphere falling as low as -80 Celsius by December. The polar vortex, guardian of the Arctic cold. The large temperature contrast then between the cold polar air and the warmer air at mid-latitudes leads to a jet stream. This is known as the polar night jet. These strong westerly winds circling the pole form the polar vortex. Think of this as a giant spinning top of cold air locked in place by fast winds. Changes to the polar night jet can affect the weather lower down in the troposphere. It works in tandem with the more familiar jet stream several kilometres below. When it's strong, the UK tends to have mild, wet winters because the jet stream flows steadily from west to east, bringing Atlantic storms. But if the polar vortex weakens, this can all change. The troposphere is full of Rossby waves. These planetary waves form as a result of the Earth's rotation and lead to giant meanders in the jet stream caused by mountains, land-sea contrasts, and by changes in large-scale weather patterns. Rossby waves with the greatest spatial scale are able to push upward into the stratosphere. If they grow strong enough, they disturb the polar vortex. The mechanics of an SSW. So what happens during an SSW? As the waves rise into ever less dense air, they grow to the point that they break, like the breaking of waves on the seashore. This breaking exerts a drag on the westerly flow of the polar night jet in the stratosphere, slowing down those westerly winds. If the disruption is severe, the vortex can weaken or even reverse direction from westerly to easterly. Winds within the weakened jet slow down and turn towards the centre of the vortex. As the air converges, it descends. Temperatures in the polar stratosphere can rise by 50 degrees Celsius in just a few days, a staggering change. But this warming isn't because of heat being added from below, it's due to air sinking over the pole, compressing and warming. Meanwhile, the vortex fragments or splits into smaller lobes and can be displaced off the pole. There are two main types of SSW. Displacement events, where the vortex shifts off the pole, which can lead to it eroding over time, and split events, where the vortex breaks into two smaller vortices. How does this affect our weather? Why should something happening tens of kilometres above us matter? Because the atmosphere is a connected system. What happens aloft influences what happens at the surface. After an SSW, the polar vortex weakens or even reverses, and this disruption can ripple downward over 2 to 6 weeks. The stratospheric westerlies support those in the troposphere. Although there will still be a westerly impotence from temperature gradients, the usual help from the stratosphere can be taken away as a result of an SSW. The jet stream, which normally flows in a relatively straight west to east path, becomes wavier and slower. This change allows blocking highs to form, large, stubborn areas of high pressure that sit over regions such as Scandinavia or Greenland. These blocks act like a traffic jam in the atmosphere, diverting the usual Atlantic storms away from the UK. So instead of mild, wet weather, we can get cold, dry easterly winds from Siberia or northerly flows from the Arctic. But the impacts aren't uniform. Timing matters. The cold often arrives 10 to 20 days after the SSW begins. Duration varies. Some cold spells last a week, others persist for a month or more. And it's not guaranteed. Other climate drivers like the North Atlantic Oscillation and El Niño Southern Oscillation can amplify or counteract the effect. In short, an SSW tilts the odds towards cold, but doesn't guarantee it. Think of it as loading the dice for winter extremes. Historical examples. Some examples of how SSWs can turn our weather upside down include January 2009. A major split event led to prolonged cold across Europe. After the SSW, the UK saw a prolonged cold spell through February, with widespread snow and temperatures well below average. Schools closed, transport was disrupted, and it was one of the snowiest winters in decades. Early 2013, a displacement event which was remarkable for the duration of the resulting bouts of cold weather across Europe and the UK, stretching from January to Easter. February 2018, the famous Beast from the East. Following the SSW in early February, the UK experienced severe cold and heavy snow by late February and through March. Temperatures plunged, snowstorms hit large parts of the country, and wind chill and freezing rain made conditions brutal. As the Northern Hemisphere has a larger landmass compared to the Southern Hemisphere, Rossby waves and therefore SSW events are more common in the Northern Hemisphere. In fact, the first time a major warming was observed in the stratosphere in the Southern Hemisphere was in September 2002. Forecasting and predictability. Can we predict SSWs? Modern models can often spot them 10 to 14 days in advance, but the surface impacts are harder to pin down. Meteorologists look for signs like strong wave activity and anomalies in the jet stream. Still, uncertainty remains, especially in how long any cold pattern will persist. Climate change and the future. Could climate change make SSWs more frequent or intense? Scientists are investigating. Some studies suggest that shrinking Arctic sea ice and changes in snow cover could amplify wave activity, increasing the likelihood of SSWs. For the UK, this could mean winters become more unpredictable, alternating between stormy wet spells and sudden cold snaps. Sudden stratospheric warming is a dramatic reminder that our weather is shaped by forces far above our head. From the polar vortex to Rossby waves, these interactions show just how interconnected Earth's systems are. If you enjoyed this in-depth look, hit like, subscribe, and tell us what we should explore next.